distinguished professor at Texas A&M University. He's earned his PhD degree from University of Washington, and he's has also held several faculty positions at University of Minnesota and University of Cambridge. He served as editor-in-chief of the Astrophysical Journal and is currently co-editor of the Annual Review of Astronomy and Astrophysics. So his research is focused on evolution of galaxies, star formation of galaxies, and extragalactic distance scales. And awards for his work include the Proper Cosmology Prize, the AAS-AIP Daniel Heinemann Prize in Astrophysics, and the Gold Medal for the of the Royal Astronomical Society. And together with Fiona Harrison, he co-chaired the Astro2020 Decadal survey of astronomy and astrophysics, and he's going to present the results of this survey. So thank you very much, Rob, for coming.
Right, thank you.
Looking forward to hearing you. So.
Thank you. Let me get my wires straight. So thank you. It's the first time in my life that I get apologies. The turnout for the talk might be poor because it's so early. It's 6 p.m. So people aren't ready. I'm really a professor of committees these days. So what I'm going to talk about is, indeed, every 10 years, I'll explain this in a minute, astronomy, as many fields does, sets out a vision and writes a report for the Congress of the US and the agencies recommending priorities in astronomy for the coming decade. And our report just came out in November. And I'm really flattered that here, outside of the US, you'd be interested for me to talk about the results. What I'm going to do, I know we have an audience on Zoom as well. Since you come, I think most of the faculty here are familiar with decadal surveys. I mean, Europe has its ESA Voyage 2050 studies, Horizon studies, and you had an Astronet, right, exercise about 10 years ago that's modeled on these surveys. But I thought I would begin by talking about the process. What is a decadal survey? Why do we go through all this work? Why are they important? Talk about the process, how they're put together, and then I'll talk about our recommendations, beginning with the science priorities, and then taking you through the various recommendations all the way from the multi-billion-dollar space missions that are recommended, ground-based telescopes, down to infrastructure and things that need to be done to make the profession a better place to work. So we'll, this is a 700-page, about a 650-page report. So I will go fast. I mean, I won't go fast. I'll be done. It will be 50 minutes, I guarantee. But I will. The compression will be very high. But I'll try to, you can ask questions afterwards. I can stay for that. So, what is a decadal survey? So this is undertaken by the U.S. National Academy of Sciences. The Academy of Sciences in the U.S. is more than an honor society, where scientists give each other prizes. It was established by Abraham Lincoln for the express purpose to bring together the best scientific minds in the country to advise government on, back then during the Civil War, to give advice on that, but in all areas ever since. So this is serious. If you get elected to the National Academy, you get sign up for work, and a lot of it. But probably the most important role are these surveys. So I said what they accomplish every 10 years. They provide prioritized recommendations to government and agencies. And in fact, for Congress are now, at least for astronomy, are required. We must do one as part of the NASA Authorization Act. They don't want NASA to go more than 10 years without adult supervision. They want the community to have an iterative step of setting priorities for them. And I'll say a little bit more about that later. Astronomy for the National Academy of Science was the first astronomy survey. We paved the way. in 1965, what's called the Whitford Report. Our report is the 7th. They've been every 10 years ever since. So they work, obviously. And the character, I'm going to show you in the next few slides, the character of these surveys is completely different from what it was like in the 1960s. This is the listing of the complete committee for the astronomy survey. This is another committee, so don't bother with them. 8 people, all white, all male. I'm looking at the names, all like gray, like me. They met, made their decisions, and if there was information the 8 of them didn't have, they would go down the hall and ask their friends, right? So not ideal, but in fact, an amazingly good report at the time. The world has changed. So here's the first of 3 pages of the members of our committee. I have to mention my partner in crime. There were 2 chairs of the committee. This is Fiona Harrison, PI of New Star, professor at actually professor and dean at Caltech. This is the main so-called steering committee, 20 members, diverse completely. I won't go into more detail than that. And then we were our committee was advised by 13 expert panels in different scientific and technical areas. And don't try to read them, but just let me take you through the 3 pages. All in all, 131 individuals on panels, not all members of the National Academy of Science. I mean, good, incredibly diverse range, people from academia, from the research community, even industry, and so on along the way. I'd love to show you a group photo of the committee, like we did at our conference today. We did get one before the pandemic hit of everyone, but in fact, I put this up because this is how I remember my committee. We were supposed to meet 6 times over slightly less than 2 years. We managed to just get in 2 meetings, 3-day meetings together. And the 4 meetings after that were replaced by somewhere between 50 and 60 Zoom meetings, which, over, and many of, all day, there were, we had weekly 1.5-hour meetings and sometimes 2-hour meetings. And then we had many sets of all day, meaning for Zoom, that maybe 6 hours. You'll notice we have one spy on our committee, Tim DeZeu from Europe. In 2010, the spy was me because I was at Cambridge as a Plumian professor at Cambridge at the time. Although, of course, I still had an American passport, so I don't really count. Anyway, all I can say is try, if you can avoid, don't do this over Zoom. Consensus report means every member of the committee has to agree with every one of the roughly 40 recommendations, word for word, or we can't finish, you have to finish. And that took a little extra time by Zoom. I'll leave it at that. And so it's obviously a diverse set of people writing the report, but in fact, that's the tip of an iceberg. At least over the last 10 or 20 years, we've tried as much as possible to involve the entire astronomical community or those interested in doing this. And the primary mechanism by that is before any of the panels in a given area meet, we put out calls to the community for white papers. And you're familiar, again, with this, I'm sure, from the ESA process and Astronet and so on. So for example, before we began the process of prioritizing science, we received 573 white papers from the community. They're all online. They're beautifully written. They're only 5 pages limit, but they're beautifully written summaries. You could do better. You could not do better, teach a better graduate journal club course than to have a course simply presenting white papers from this. They sum up And then later, what this means, we had a second case where members of the community, usually in large groups, could write papers advocating for a particular project. And also, I'll talk about later, we had a special panel assessing the health and the state of the profession. And that attracted among these about 70 white papers as well. And again, all openly available on the web for you to read. This is the foundation material. This is roughly, what is it, 870 papers. There were about 6,400 unique authors to these papers. The American Astronomical Society has 8,000 members. So, you know, most of the people in the country did either author, co-author, or endorse at least one paper, although there were many people, many Europeans around the world also, many of you may have participated as well. So, but that gives you some sense that, and it's very powerful and helpful to us. First of all, this is the raw material. Almost everything that came out of the survey you can find suggested in a white paper. Every white paper was assigned to at least one of the program panels, and their instruction was their first meeting was to be devoted to presenting and discussing each paper, either, not always individually, sometimes in groups of similar, you know, papers saying the same thing. And we can go to Congress, our government, and say, you know, this isn't Rob Kennicutt and Fiona Harrison's, you know, thoughts or 20 people's thoughts. These really, of course, the whole community didn't agree to it, but you know, everyone who wanted was able to participate, and those inputs really are the raw material. So the process was white papers were taken up by panels. Each panel wrote a report, which appears in the main volume as an appendix. I'll go through that later, one step at a time. Each panel then made recommendations in its own area to us. And then, of course, we assimilated, you know, each panel wanted 2 times more than we could possibly do, right? And multiply by 13, and the main committee then makes prioritization based on those inputs. So I think I'm done with talking about process, and I got to move on a bit. So, well, not quite. So maybe not surprisingly, now I told you the first of these was astronomy, but in fact, nearly all of NASA's science divisions now do decadal surveys, and many other, there's a physics decadal survey, there's a plasma physics decadal, I think there's a chemistry decadal, and so on. So, you know, why have they become so important? The key reason is they have impact, they work. The Congress is immensely appreciative of the job we do, in large part because we make difficult decisions. If you add up the money, the cost of everything we recommend for the coming decade, it's something on the order of $20 billion. That's what NASA and NSF, actually, mostly NASA, obviously, and Department of Energy spend nowadays on astronomy. I don't know what this, we never could add up the cost of what everything that was proposed to us, right? Because as for reasons I'll describe, we have to go through a formal costing process to do that. But it's easily $100 billion, excuse me, dollars. So the idea is to present Congress and do the infighting, if you want to think of that, prioritization in public within our community, and get the community behind the recommendations, rather than leaving it to individual government to essentially fight over pet projects. And so it takes a big burden off of them. And history shows that the surveys are effective. Does everything that gets recommended in a 10-year period get done? Absolutely not, because I'll describe, we ask for more. You always ask for the maximum you expect you might get, or projects, say like James Webb, take longer, but generally the top recommendations are followed and respected. And we've now had meetings with Congress, and we're beginning to learn how that part of the process works. Okay, so how do you do that? So I've just told you, you're given this impossible task. Our community is very imaginative in thinking about ways to spend money, and do astronomy, right? What everyone, of course, thinks their subject is most important. How do you do this? I'll explain it first in a budgetary sense. So at the beginning of every survey, our first meeting is devoted to presentations from the agencies, and they basically give us our marching orders, describe the task before us. And in this case, amazingly, I think partly because it was pre-2019, all three agencies, even our National Science Foundation, and the Americans will understand the significance of what I just said, told us to be ambitious, aspirational, inspirational. Those are direct quotes. Right? I didn't make those words up. But of course, you have to be responsible. You can't, be ridiculously, if you propose way more than is possible, they're going to ignore your priorities. So you have to be realistic, responsible, achievable, sustainable, and so on. So how do you do that? Well, the agencies do quantify what ambitious and aspirational is. They give you, I'm going to put this up, don't read this in great detail. This, for example, is actually the so-called budget wedge. This is the cost to the National Science Foundation Astronomy Division if over the next 2 decades, if they would implement every recommendation made in the report. And so they give you a range of allowed amounts you can ask for year by year. There's always a pessimistic scenario, which is usually inflation only, last year's budget plus inflation, although this year that would be a lot of money. And then the top bound, it varies from survey to survey, but it can be anywhere from 3% to 5% a year. For reference, a 7% increase every year for a decade would double your budget, and we've never been given that, even though there was talk at the time in Congress of possibly doubling the budget of the NSF over the next 10 years. So we had a fairly good range. And so what we do is we give a program that just fits under the most the most we could possibly be allowed to spend. It's crazy, right? Why would you ask less? As the director of NASA Astrophysics said, if you ask for very little, we'll probably give you what you want, And so what you do, but then, so you give you'll see a very ambitious program, but we have then, along with it, what we call decision rules. Here's what you should do, if your budgets are less optimistic, or if a project overruns, or if Europe decides to build the same thing quicker, and et cetera. So we give lots of advice on it, but importantly, in the great detail, we leave details of implementation to the agencies. We cannot anticipate what will happen, 10 years ahead. We did not know if James Webb, would launch successfully or work. And as I'll show you, we already, one or two of our recommendations already are obsolete because of changes in a minor way. Okay, finally we go. So on to the results of the report. You can call this a pyramid if you want, or you can think of it looking down onto a pathway, either way, with your feet at the bottom. This is actually a guide to the various chapters in the report, but it also sort of describes the structure. The ultimate goal is to do science. And so you begin, the whole first year of the survey almost consists of setting science priorities, something at our conference we spent 45 minutes discussing already in miniature. And then when you start considering proposed projects, you can hold up a yardstick and say, how does each proposed mission meet the scientific objectives that we have set? You don't want to build something that's beautiful and shiny but won't answer any questions, right? That's the idea. Then we have our recommendations. At the top end being the multi-billion-dollar space projects, the 30-meter telescopes on the ground, the VLAs and so on. Then intermediate scale projects, and finally, for the very first time in this survey, we created 2 new committees. One which prioritized the little science, I'm going to put it that way, not to be derogatory. Things like individual grant programs, technology development, data science, laboratory astrophysics, and so on. The things that often get overlooked and don't cost much money. And then a chapter on the state of the profession and societal impacts. What things do we need to do, both as a professional society and in terms of agencies, of improving the workplace and making astronomy a more attractive place to work in a profession that reflects our society in terms of the demographics of our profession. So what I'm going to do, normally when people get this book out, they jump to the chapter that has tables. It's like the football tables after it was Real Madrid ahead of Barcelona. And well, did the radio telescope win this time or not? And, you know, I think people almost bet on these things. In fact, to combat that, our report is written from the bottom up. We're going to begin very briefly again, talking about some of the foundational recommendations, and then I'll jump to the big projects after that, right? So, but first the science, right? So I said science trumps all. So I'd forgotten we hadn't gotten to that part yet. So again, so the process here in Capsule is we got 573 great ideas on what the most important science should be. We formed 6 panels. You might have seen their names earlier: cosmology, galaxies, exoplanets, and solar system, astrobiology, etc. So divided in areas. They each got, as you can see on average, about 100 white papers to digest. And they wrote a 25-page chapter that summarizes in great detail what they think the most important science would be, just like we tried to do this morning in the conference. But then for our report, we can't have 573 recommended projects. No congressional staff will read that. None of us maybe would read that. So we asked each panel to give us 4, sort of categories of priority areas for the future. And these are questions that conceivably can be answered over the next decade. And then for each panel, give us a discovery area, an area where maybe more high risk, maybe more uncertain, but where some very exciting development could really bring about a revolution. And so, for example, in 2010, I can think of 2 of the discovery areas. I think it was 5 panels. One was astrometry, which, bingo, right, Gaia. And another was gravitational waves, bingo, Nobel Prize. So, and reionization was one. I can't remember each one's, and we'll talk about ours later. Anyway, and that's what and then when these came to the main committee, then the main committee, our main committee went to work. And even here, you really don't want to write a 30-section science chapter. But what we found was these 30 items could very nicely be encapsulated into 3 very broad science themes. I won't call them, I'll be taking you through them. And then finally, this is a little bit more complicated. So this is mainly science themes for an astronomical audience, for ourselves. And then we wanted to distill, once we knew what the science projects were, we wanted to have 3 sort of scientific goals, which would be stated in a way that could be very appealing to the public and to Congress and so on, and connect very well to the recommended missions. Right? They're separate from these, but each one is a subset of one of these. Let me just show you. I'll give you the 3 examples and so. So in no particular order. So our first theme is world and suns in context. It recognizes 2 things, really: the enormous advances in our detection and characterization of exoplanets over the last decade, Corot, Kepler, etc., and all the work being done on atmospheres and so on. An utter revolution, over 3,000 new planets discovered over the last decade, and the revolution that Gaia and Corot and Kepler with astroseismology that Christina has been talking about for those at the conference has wrought over the last decade for stellar astrophysics. And the 2 cannot be separated. If you want to define a habitable planet, you darn well better understand the stellar activity of the host star. And we're generally talking low mass stars, and they are active. So I'm going to not take you. The revolution that just began a few months ago with the solar telescope. And so there are obviously a series of specific questions to be answered, but I don't have time today to go through them. What is anyway, we think as productive as the last decade has been, the next decade, that wave of discovery will, Gaia is the gift that will keep on giving. We're going to continue. This will continue to be a cutting edge subject. For our priority, we set a goal for 20 years, really, probably the most ambitious goal of our survey and maybe any decadal survey in astronomy. And that is basically the first step to addressing the question, are we alone, to set the goal of imaging planets, Earth-like planets, in the habitable zones of their parent stars. Image, I mean, take family portraits of solar systems, an image where you see the Earth thing, the pseudo-Earth and its companions, and stick the light of the planet, which you image separately from the parent star down the slit of a spectrograph, so you can do spectroscopic characterization of the composition of the atmosphere and look for ozone, whatever your favorite biomarkers are, signs of life. We're not talking little green men or women, we're talking about life, trees and chlorophyll, things like that. We think it'll first be done from the ground by the ELTs. It seems that with chronographs, it'll be possible to detect planets around M dwarfs for stars, of course, pretty close in their habitable zone being, by the way, where liquid water basically exists on the surface. Doesn't mean that's likely to hold human life, but that's where the step one. But from space, we were convinced that technology has evolved to the point, and that within 15 to 20 years, we will have enough candidate G-type stars, sun-like stars nearby, with planets roughly the size and mass of the Earth, 1 AU from those stars, to do the same thing from space for about 25 stars, which, phenomenal if we can do it. So that is the main goal. You will need other wavelengths, habitability, you need to understand activity, so obviously X-ray observations, and a ton of astrochemistry and astrobiology lab and theory work, which is lacking. Needed for ALMA and other things too. And to study the formation of the planets and the submillimeter radio as well. So that's the first one. The second theme, back to themes now, was named New Messengers in New Physics. This is basically the marriage of the revolution in time domain astronomy from LIGO, Virgo, and the future work on transients from the Rubin telescope and so on, gravitational waves, with dark energy, the grand challenge questions in fundamental physics in cosmology. Again, the theme is paramount, as we'll describe at the end of the talk. We probably will have the capability by the end of the decade to detect the B-mode polarization and the signature of inflation, if it's there in the CMB. And then when the Rubin telescope comes on, you've heard the statistics, 100,000 transient events per night. And you want the ability when gravitational wave detectors detect a neutron star, a black hole merger, to have electromagnetic follow-up instantly. This is really an international effort, obviously. And I'll talk about IceCube at the end. The priority area that goes along with that, we call new windows on the dynamic universe. This is the first item on the wish list that does not involve building a giant telescope. What we think the main need here is not for huge X-ray or radio or optical telescopes, is you want panchromatic coverage of the electromagnetic spectrum to go with gravitational waves, cosmic ray, Cherenkov facilities, so on. You want to be able, when these events occur, especially the most explosive events in the universe, the ability to follow up and coordinate across wavelength We do reasonably well right now, but we are vulnerable. If the Swift satellite would die, we would not have continuous gamma ray monitoring capability, for example. And so the recommendations here really are aimed not with any one big thing, but really to create essentially make sure there are observational facilities on the ground and in space that can follow up, and the data infrastructure so that you can very rapidly, combine these data and so on. And here are the elements that are in it, but I'm going to come back and talk about each of these individually. And I've got to hurry up. Finally, the last one ought to be familiar to people who are attending this conference. If I had been on the panel, I guess this is what I would have said. So there was a galaxy, and there also was an ISM panel, and a stellar populations was part of a panel. And basically, we merged those recommendations into something called cosmic ecosystems. This is not really a new theme for decadal surveys. It's what NASA calls cosmic origins. The question is, where do we come from? Search for life and planets is one thing, but this is all about what are our origins? How did stars form? How did galaxies form? How did the universe form? But with the new recognition, really, appreciation now that those aren't three different questions. As someone who spent his life understanding star formation, I've come to realize I darn well better understand galaxy evolution. I'm not going to solve star formation without understanding galaxy evolution. You will never solve the galaxy evolution problem without understanding. There is a multi-scale range from the scale of a supernova progenitor, right? A single supernova can disintegrate a galaxy. Every galaxy in the universe today began as a quantum fluctuation during the epoch of inflation, right? These things are connected. Numerical simulations have shown us in principle how these things are connected. So we think that there will be enormous progress, beginning, of course, now with Webb, which is going to produce the detailed history, time-lapse history of galaxy formation and evolution, followed by these wide field telescopes that will give spectra and imaging for samples of, tens of millions of galaxies, and hopefully progress in simulations. And I'll talk more about the physics of this now in this slide. So what do we need to do all that we don't have now? We've got Webb. So the first big item, obviously Webb, that's not a recommendation. If I could sum up the discussion this morning at our conference, I would say we have simulations. I'm going to repeat what we heard. The simulations can actually make realistic looking galaxies today, but they make a lot of approximations. It's not ab initio physics in them. The baryonic physics is recipes. So when Webb gives us this history of metallicity in stars and everything else, we'll have simulations that can get it right if you tune the parameters. But the key missing ingredient, these are galaxies are ecosystems. They're feedback cycles. Stars form, but they give their energy back, and so on. It's the energetics. This system is powered by transfer of energy, and it's through diffuse intergalactic medium, circumgalactic medium, interstellar medium. Thin gases, plasmas, faint beyond the spectroscopic abilities of even Hubble and most of the telescopes we have on the ground, except in very special areas. So what we need is a telescope with the aperture, with the wavelength coverage Hubble, but at least 6 meters in aperture to be able to do quasar absorption spectroscopy through thousands of sight lines over the sky with 100 times, probably about 100 times more sensitivity, not just from aperture squared, but from the detector, improvements and multiplexing that you could get. And this problem needs multi-wavelength, coverage as well. So that's the third, unveiling the drivers of galaxy growth. Okay, so here we go. It says 10 minutes to go, and I'm got good missions. Okay, this has happened again. So let's talk about very quickly, starting with the foundations. I'm going to start with the people this is probably the most quoted single sentence from this report. I mean, I've seen it quoted at least 20 times. The pursuit of science and scientific excellence is inseparable from the humans who animate it. We pointed a panel to look at every area's education, demographics, workplace environment, the whole shebang. And they focused largely on diversity, equity, and inclusion. And the main panel also looked at things like benefit to the nation, technology spin-offs, outreach, and so on. This is an area where many aspects of our profession have improved over the last decade in the US. Female representation at all ranks except the very top have improved. There's a problem with mission PIs, heads of department, and so on. So we have recommendations, but improvements on the way. Hispanic enrollment in the US sense, mainly Mexican American, is also increased dramatically in a way that should come to equity in another decade or so if it continues. African American representation pathetic, and still equally pathetic over time. There's something wrong here that has to be fixed. Native American, similar. Sexual harassment makes front page news of newspapers over the last decade. It's an embarrassment to the profession and should not be tolerated, etc. So a few recommendations. You look at the report, encouraging you to read the report actually. We discovered that, we asked the question, is grant money, is telescope time being distributed equity? Is there unconscious bias against young people, against women? And the agencies, except for Space Telescope, they said, how do we know? We don't collect those data. They were beginning to collect it for male, female, but nothing else. And one agency said, we're not even allowed. It's against the law, which was incorrect, it turns out. So we have recommendations getting NASA, NSF, and the DOE, at least at the astronomy level, to get together, talk to the National Institute of Health, which has been doing this for decades, and be like them. We have recommendations on improving diversity of project and mission teams, and last week, the Academy released a study commissioned by NASA, a book that explains how to do that, and I won't go into detail here. There have, in terms of particularly African American representation, but also underrepresented groups generally, there have been programs in the past, for example, giving internships to undergraduates at students at minority serving institutions to be able to do research internships at Research One universities, that all of the data afterwards show have been incredibly effective in terms of keeping people in the pipeline, and but are terminated every time there's a budget cut. Those we recommend be reinstated. In fact, I'm happy to say most are already, etc. We have a statement. Basically, harassment and discrimination should be treated as a form of professional misconduct, just as bad as if you faked your data. The National Academy itself has done that, and that's complicated. I won't get into it, especially you won't know what Title IX means here if I told you about it. Community relations has to do with making sure that the people who have a vested interest in the sites of observatories are consulted. That's a very complicated can of worms in some cases, but we basically argue subjects like archaeology, where people do digs in Native American burial sites, have figured out a way to work with the communities by setting their own standards of how they should behave and never making plans without, from the very beginning, consulting with the indigenous communities and so on. Astronomers should learn from them and other subjects that do it. That's them. Dark sky, this has to do with satellite constellations, protecting the, I won't say more now. And then what we've been talking to Congress a lot, they are really, they see us as having a key role in inspiring young people We already do a lot of that to become not just astronomers, but engineers, doctors and so on. So there's that. In terms of infrastructure for research, I really am going to just go, soundbite because I've gone hopelessly behind here. The grants program, particularly in the National Science Foundation, has become ridiculously oversubscribed. It's extremely difficult, so we talk about that. Much more can be done to train our young people on big data. We know SKA and everything else. There's a wave of even more data preparing for that. And then I'll just say technology development, lab measurements, theory, making sure these are recommendations, just not to necessarily provide money, but recommendations on how to allocate the money more fairly. Okay, so let's get to those big projects. And I'm probably going to almost a top hour, but I'll finish then for sure. We have, I'm going to start with space recommendations first, and then ground. The one sentence summary of this slide is to say, this is a list of all the missions of projects that were approved by previous surveys and at the time had not yet started, like James Webb and so on, and simply arguing, make sure you save enough funding to support the data analysis and so on, operations of those facilities before you start something new. That's a big issue, it turns out. So we're going to begin with space. We actually, over the decade, recommend that development be done on 3 projects, one in the Hubble-like project, one in X-rays and one in infrared, and then some mid-scale operations. But let me just jump into it. So before every survey, NASA actually does prepare the field by developing proposals for missions. 20 years ago, the #1 recommendation was James Webb Space Telescope. 10 years ago was the Nancy Grace Roman, or WFIRST, Space Telescope, which should launch mid to late decade. This time, NASA commissioned 4 teams to prepare detailed proposals for us. HabEx and LUVOIR are large ultraviolet, optical, and near-infrared telescopes of different apertures, 3 to 4 meters for HabEx, and I'll talk about that in a minute, and 8 or 15 meters for LUVOIR. The idea was to do any science that Hubble could with a much larger aperture, but have coronagraphic capability to with high contrast imaging at the level of 10 to the minus 10, to be able to detect, an Earth next to its sun. LUVOIR does that exclusively with coronagraph and a very sharp diffraction limit. HabEx has a formation flying star shade that would create occultations plus a coronagraph. LYNX is a very ambitious X-ray, spectroscopic and imaging observatory. Origins, a far infrared, mid to far infrared, cooled, large aperture infrared imaging and spectroscopic observatory. Normally, the expectation is we would rank them 1, 2, 3. We would have to choose between HabEx and LUVOIR and rank between them. NASA also asked us whether we should recommend 1 or more missions in the $1 billion class. Those are called probes. Examples from the past, COBE, Kepler, if you inflate them to present day dollars. And they had 11 teams present proposals to us, 10 of them orbiting in space, 1 on the far side of the moon. So what did we do? Well, we looked at these areas first. Again, science. You always do science first. And we found all 4 of those big missions, I'm back to big missions, would do paradigm shifting science on their own, but no one by itself could solve any problem entirely. In other words, a multi-wavelength approach was required, especially for the ecosystems and new windows and new messengers, new physics themes. And in fact, we got quite a bit of pressure from the community to say, why don't you recommend everything, right? Wouldn't that be a wonderful world? Not as outrageous as it sounds, because 20 years ago, that was done. There were 4 missions flown within a space of 13, launched within a space of 13 years around the turn of the century. And 3 of the 4 operated simultaneously for several years. Chandra and Hubble are still operating, Compton Gamma Ray Observatory and Spitzer. And I think anyone who's used them will agree that the sum of the science from those 4 missions being close in time vastly exceeded the sum of the science from all 4, take each one and add it if they'd been done 10 years apart, say each. So why not do it again? Well, that bubble burst when we went out for costing. NASA requests trace means. The government, Congress requires any large mission we recommend has to go through an independent costing exercise, basically to make sure the people who wrote the proposal did their engineering right and were honest, to be honest. It looks at cost, risk, and technical readiness. Here's a summary table for those 4 missions, and cost estimates ranging between $9 and $17 billion. Compare that to Webb at 11, and nearly got canceled because it was thought to be way too expensive by Congress. No, we might get $10 billion over a decade if we were incredibly lucky. In fact, these 3 were instructed to come in with a design at $5 billion, and none of them made it. They were allowed to go over. I mean, so that this wasn't a factor of 2 error. So that was one problem. If you try to do, one of these plus these 2, Congress would laugh. They would do nothing, right? The other is time. Okay, let's do them one at a time. Let's cancel all the other decadal surveys. Well, they take about 20 years apiece. So if, say, you do this one first, and then you do this one, and then you do this one, it'll be what, 2065 or something. I don't know if any of you will still be working then. I won't. I know I'll be lucky to be above the ground then. So just doesn't work. So obviously we couldn't recommend 3 of the 4, and we decided we couldn't recommend any one right now. Of course, we can't say that and stop. We have to have a future. But why? We weren't ready. These costs showed that a lot more work needs to, back to the drawing board. First of all, we thought, it turns out for detecting exoplanets, none of the HabEx designs had an assurance of giving us at least a dozen, being able to image a dozen Earths. There are enough of them close enough to do it. LUVOIR, this is the small LUVOIR, by the way, the big one we even try costing, would give us 100 or more, but is more than you need. So I'll tell you what our recommendation is in a minute. So what we did, we had to thread the needle. And what we've said is we set as a top priority a planet imaging, a UV optical IR of about 6 meter, Goldilocks, not too big, not too small, just right. That we're quite sure, this is the panel by the study this Marshariki chaired, can high probability of doing 25 planets and do all that wonderful cosmic web spectroscopy. Any science Hubble does, it'll do, much better, general astrophysics. That's our top priority. But that instead of saying now, we approve you, no matter the cost, go ahead, right? Is take another 5 years, figure out and design your new telescope, get the 2 teams together, come up with something, cost cap 11 billion, that's it, never go above, and decide after the 5 years, convene probably a mid-decadal, and if you convince them, then the green light. Now Congress has to agree to invest $500 million, $800 million on a design study, but that's there. But at the same time, just so we don't have to do this every 10 years, in the second half of the decade, for links and origins, drop the names, cut your cost by a factor of 2 to 3, come up with something, a D-scope, basically, and do a study of that. And then you'll be ready. You'll have that study for the next decadal survey, and a decision can be made whether to, if this goes, if this one goes ahead, you go second, one of these will go second line. Or if this fails for some reason, suddenly you're front of the line. We'll see whether it works. But NASA had been developing an approach somewhat like this, and so far so good. So I'm sorry, I can't say. Why did we put the exoplanet mission number 1? It's the excitement of the science and the fact it will do, like Hubble, it's incredibly versatile. It'll answer essentially almost all the science questions in the survey. And so I'll leave it at that. We recommend, I already talked about that, we recommend a time domain program, just a set of small satellites to ensure continuous coverage and data infrastructure to be able to coordinate between platforms on the ground and in space. For the probes, we decided we could have chosen one, we could have had an open competition, or we could have recommended an open competition with selected areas. We chose door number 3, and that is go out for studies for a $1 billion mission, either IR imaging and or spectroscopy, recognizing that Europe and Japan have canceled the Spica mission, and also separately a targeted X-ray probe that complements Athena. This is the first big change. ESA announced recently, Athena, I think they've announced, I hope I'm not, breaking a secret. Athena will be delayed and descoped probably. And so we're going to drop that part, but complement still Athena science in some way. For the ground, the story on the ground in Europe. Of course, you're building a 40-meter ELT. The top recommendation on the ground is that the NSF join as a partner in the 2 US programs, 30-meter telescope, that's its name, including University of California and Caltech, and a number of countries, Canada, and so on. And the Giant Magellan Telescope, which is mainly a university collaboration, a 7-mirror, 24-meter telescope. The reason, again, for being number 1, huge discovery space with adaptive optics. You get gains over Keck of a factor of 40 to 80, resolution better than Hubble, obviously, and so on. And incredible versatility of scientific applications. We don't think those projects already have partners. We recommend that if it's possible, and both projects are ready, NSF essentially invest as a quarter partner in each. If one project is not viable, get as much, up to half the time on the other, with some conditions. But that would give the community 180 nights total on 2 telescopes, one in the north, one in the south. We don't know if the 30-meter would be in Hawaii or La Palma, but in the north. So priority number 1 is that. Priority number 2 is a much lower cost mission project, a cosmology experiment, CMBS-4, stage 4 cosmic microwave background experiment. It's designed to detect the inflationary signatures in the cosmic background using radio telescopes at the South Pole and in Chile, big arrays. We like the idea of another Nobel Prize for astronomy. I mean, this is good science. And the maps, it's sort of like a Rubin Observatory, an LSST in the radio, imaging the southern sky between a millimeter and meter. Best will be those data. Of course, you can't make the polarization data available to everybody until they do the experiment. We can make the rest of the data available for all sorts of scientific applications. It would be a collaboration with the Department of Energy and NSF, $300 to $400 million each. Finally, for the radio astronomers, there's a very ambitious proposal to replace both the very large baseline with a transcontinental array of telescopes that would offer order of magnitude improved resolution, sensitivity. It's sort of the US component of the, if you think of SK in a very broad terms, similar approach, but at higher frequencies, of course, quite different. So the survey recommended that a study of this go forward. And our recommendation is like that of the maturation program. We can't afford to build it now. It's a price tag estimated at $3.2 billion, or 2.5 if NSF has to pay for 3/4. But do a study, look at options of building it in phases, maybe down scoping it a little bit, and then if build prototype antenna, so on, answer those questions. And by mid-decade, if all of the indications are good and ELTs and CMBS4 are on the glide path, it comes right in, or in principle could even come in a little earlier, depending on the situation with the other projects. Done almost, by the way. Don't panic, Monica.